Okay, this is going to be the first of 3 videos on section 6.1, which is on power series and functions. So we're going to look at the definition of a power series. A series of the form sum n equals 0 to infinity c sub n x to the n, which is equal to c naught plus c1x plus c2x squared plus dot dot dot, is a power series centered at x equals 0. So if we wanted to write some of these terms out here, this would be c naught x to the 0 plus c1 x to the first plus c2 x squared plus etc. c sub n x to the n plus, and it keeps on going. A series of the form sum n equals 0 to infinity c sub n x minus a quantity to the nth power, which is equal to c naught plus c1 x minus a plus c2 x minus a squared plus dot dot dot, is a power series centered at x equals a. So here wrote this out. This would be c naught x minus a to the 0 power, so that's just going to be the c naught, plus c1 x minus a to the first power, and etc. Okay, so we're going to look at 2 power series, and we're going to figure out where they're centered at. Now, before we get into that, x to the 2n plus 1, using properties of exponents, we could write that as x times x squared to the n power. Okay, and so you can certainly have, instead of an x, you could have an x squared in your power series. So the first power series we're going to look at is going to have a power of x to the 2n plus 1. So the power series, what we're going to do is we're going to determine where the following power series are centered. So the first one, we're going to look at the sum n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. Okay, so essentially what we're going to do is we're going to look at the x, whatever the exponent is, the x to the 2n, and what makes the x 0 is 0, so this is going to be centered at 0. The next series we're going to look at is the sum n equals 0 to infinity of x minus pi to the n power, all over n factorial. So what makes the x minus pi to the nth power is going to be pi, and so this one is centered at pi. Okay, so we're going to be interested in where these converge, and also we're going to talk about the radius of convergence. Now, we might have had a couple of problems maybe snuck in here or there where we talked about a radius of convergence. So let's go ahead and do some examples in just a moment here. We need to get some definitions out of the way. Okay, so we have a theorem, and it says the series sum n equals 1 to infinity. It could certainly be also 0. It doesn't have to start at 1. It could be also at 0. C sub n x minus a to the n will satisfy one of the following properties. Either the series converges at x equals a and diverges for all x not equal to a. So only a, plugging in a there would certainly make every term 0. Or the second option is the series converges for all real numbers. So it doesn't matter what value of x we plug in, it will converge. And the third option is there exists a real number r greater than 0 such that the series converges if the absolute value of x minus a is less than r, so x is within r units of a, and diverges if the distance between x and a is larger than r. At the endpoints where the distance between x and a is equal to r, the series may converge or diverge. Sometimes we'll be able to tell that, especially if we have like a geometric series test. We'd be able to tell what that is. The ratio or the root test, maybe not so much, but let's go ahead and get a little bit more stuff to get, preliminary stuff that we need to get out of the way so we can start working on some problems here. And now let's talk about the radius of convergence. The power series n equals 0 to infinity of c sub n x minus a to the n power will have one of the following radius and intervals of convergence. if the radius is equal to 0 and no interval of convergence, if the series converges only at x equals a and diverges for all other x not equal to a. The radius is equal to infinity, and the interval of convergence is all real numbers if the series converges for all real numbers. And then the third possibility is some r greater than 0, and the interval of convergence is a minus r comma a plus r if the series converges on that interval and diverges on everywhere else. Check the endpoints for the convergence or divergence, and so we'll see some examples where it might converge at an endpoint or diverge. So the three possibilities for your radius of convergence is 0. That means the series only converges at where it's centered at. The radius is infinity. That means it converges for all real numbers, it being the power series. And then the third possibility is we have a positive radius, and so as long as we're within the radius of the A, where we're centered at, we will have convergence. All right, so let's work out some examples where we find the interval and radius of convergence. So let's not get too far ahead here. We're going to determine the interval and radius of convergence of the sum n equals 0 to infinity of x minus 8 raised to the nth power. This is a geometric series. Geometric series sum n equals 0 to infinity of a r to the n. This is going to converge provided that the absolute value of the common ratio r is less than 1. It is going to diverge or diverges when the common ratio in absolute value is greater than or equal to 1. Okay, so this is going to converge. This specific series, our common ratio here is x minus 8. This is going to converge when the absolute value of x minus 8 is less than 1. So this is equivalent to saying negative 1 is less than x minus 8, which is less than 1. Add 8 to all three sides, and that gives us our interval convergence of 7 to 9. And our radius in this case is going to be 1. Okay. Now the case where x minus 8 is equal to 1, that would give us x minus 8 is equal to negative 1, or x minus 8 is equal to positive 1. So that gives us x is equal to 7, or x is equal to 9, which in fact are the endpoints of our interval of convergence. However, this would be saying that our common ratio in absolute value is equal to 1, so the geometric series test already automatically tells us that we have divergence at the endpoints, so there's no need to check the endpoints. Okay, let's take a look at another one. So number 4, we're going to be given the sum n equals 0 to infinity of a sub n, x minus 8 to the n, converges at x equals 11. And then what we're going to do is we're going to determine, based off of this information, what's the largest radius of convergence, largest interval of convergence. All right, so we know that this series is centered at 8. And so we know for sure that we can go to 11, so we are given that it converges at 11, which is 3 units away. And because they tell us it's convergent at 11, we can include 11 in our interval of convergence. So, based off of this information, we can go 3 to the left of 8 to 5. However, we are not guaranteed convergence at the endpoint there. We don't know enough about the series to determine whether it converges at 5 or not, but we do know that it is centered at 8, and we can go 3 units to the right, so we should be able to go 3 units to the left. Okay. So we don't know about that endpoint at 5. So our interval of convergence here is going to be 5 to 11, including 11, not including 5, and our radius is going to be 3. We would need to know more about the seed sequence a sub n in order to have an idea of the convergence at 5. Okay, let's look at another example. Okay, let's suppose that we are given the following fact: the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n is equal to 1. So that's kind of the ratio test condition there. And that would be an inconclusive for the ratio test. What we're going to do is we're going to find the interval and radius of convergence of the following series: n equals 0 to infinity, a sub n, 7 to the n, x sub n. Now what we're typically going to be using for finding the interval and radius of convergence is either going to be the geometric series test or the ratio test. Seem to be the two series tests we use the most. Sometimes you might see the nth root tests come in there every now and then, and sometimes we'll use the nth term test for divergence. Sometimes when we're checking endpoints, we're going to use p-series tests and the alternating series test. But I would say that geometric series and the ratio test are probably what we use the most. And that's what we're going to use here, is we're going to use the ratio test. So the limit as n goes to infinity of a sub n plus 1, 7 to the n plus 1, x to the n plus 1, all over a sub n, 7 to the n, x to the n. And I'm going to go ahead and simplify this. So you would have the a sub n, the limit of the a sub n plus 1 over a sub n in absolute value is going to be 1. The 7 to the n over 7 to the n plus 1 over 7 to the n will just be 7. And then x to the n plus 1 over x to the n will just be x, and still an absolute value. And we're using the ratio test. We want to know when this converges, and that is going to be when the common ratio is less than 1. So the absolute value of x will be less than 1/7. So that would say that negative 1/7 is less than x, which is less than 1/7. So our interval of convergence is negative 1/7 to 1/7, and our radius is going to be 1/7. Okay. Because we don't know what an is, it's going to be, well, we probably can't figure out whether we have convergence or divergence at the endpoints there. So we're kind of stuck there. So we just know that from minus 1/7 to 1/7 this converges. We don't know about the convergence at the endpoints there. All right, let's look at one more example for this video. And we're going to look at determining the interval and radius of convergence. So we're going to look at the sum n equals 0 to infinity of n factorial divided by 1 times 3 times 5 times 2n minus 1. So that's going to be n factorial over kind of like an n factorial, but just with the odd numbers. And then x to the n. So this is a not geometric series, this is a power series centered at 0. And we're going to use the ratio test. So limit as n goes to infinity of n plus 1 factorial, x to the n plus 1, all over 1 times 3 times 5 times ... 2n minus 1 times 2 times n plus 1 minus 1, so that's the n plus 1 terms, divided by n factorial, x to the n, all over 1 times 3 times 5 times 7, blah, 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 all the way out to 2n minus 1. Okay, this is going to be equal to the limit as n goes to infinity. N plus 1 factorial can be rewritten as n plus 1 times n factorial. X to the n plus 1 can be written as x to the n times x, all over 1 times 3 times 5 times 7, blah, 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 2n minus 1, and then the 2n plus 1 minus 1 will become 2n plus 1. Then we're going to flip over the dividing fraction and change the operation of multiplication. So it becomes 1 times 3 times 5 times all the way out to 2n minus 1, divided by n factorial, x to the n. And then we're going to go ahead and simplify this down. So this is equal to the limit as n goes to infinity. So let's see. N factorial is absorbed, x to the n is absorbed, 1 times 3 times 5, all the way out to 2n minus 1 absorbed. So what we have left is we have the n plus 1 over 2n plus 1, and then an absolute value of x. Okay. Now the limit as n plus 1 over 2n plus 1, that's going to be a horizontal asymptote. That's going to just be 1/2. I suppose you could use the L'Hopital's rule, but we're just going to use what we know about horizontal asymptotes. And so this limit is going to be 1/2 absolute value of x. Because we're using the ratio test, we want to know where this converges. That's when the common ratio is less than 1. So that says that the absolute value of x is less than 2. So -2 is less than x, which is less than 2. So then that says our interval of convergence is -2 to 2, and our radius is equal to 2. Okay, so that was the first video. We got 2 more for you, and we'll try to keep these between 15 and 20 minutes long. So we'll see you in the next one.